Hello, my name is Sathishkumar.
And I'm Aryan Bishoyi.
Our project is about the bioremediation of textile dye wastewater. Let's begin. So, everyone likes to wear colorful clothes, but at what cost? Dyeing is a process where dyes are applied to a natural fabric, typically cotton. The thing is, textile factories use about 100 liters of water and 300 grams of salt and many other chemicals per kilogram of fabric to ensure that the fabric gets a nice and long-lasting color. Most factories that don't have the money for water treatment infrastructure have no choice but to discard their wastewater into nearby water bodies or land. This is harmful for human consumption, underwater life, and agriculture. The spread of textile effluents is a huge problem in certain Asian countries like India and Bangladesh, and has the potential to become global.
Around 20% of Earth's wastewater is caused by the dyeing process in textile dyeing factories, and these effluents are causing high environmental pollution in many countries, which can create a global impact. This study examines the organic materials that can effectively carry out the bioremediation process of the effluents in the textile dye wastewater.
So textile dye wastewater can cause a bunch of other concerns, some of which include: number one, in Bangladesh, the government has declared three rivers as biologically dead due to the effluent contamination from surrounding garment factories. Number two, 72 toxic chemicals have been identified in freshwater systems coming solely from textile dyeing. Number three, long exposure of textile dye wastewater could cause neurological dysfunction, respiratory and pulmonary diseases, dermatitis, circulatory disorder, and cancer.
Azo dyes, which account for 60 to 70% of all dyes in the industry, are known carcinogens, or things that cause cancer. Colloidal matter in the dye prevents the penetration of sunlight necessary for the process of photosynthesis. This creates plumes of invasive algae.
There is a flip side to this issue, though. Textile dye factories in South India, where my family lives, follow a typical procedure in treating wastewater from the dyeing process. First, from the wastewater collection tank, water runs through the limestone bed, where ferrous sulfate and cationic poly are added in between stages. They regulate the pH, filter the dye's water's color, and clump the contaminants together. The wastewater, now with its contaminants clumped up, is then fed to a tank full of E. coli bacteria. From the wastewater, the E. coli leave behind very saline water. Then by reverse osmosis, the salt is separated from the water. There are some challenges to this treatment process, such as: number one, the infrastructure is very expensive, so not a lot of factories can afford it. Number two, the E. coli tank needs regular feeding and maintenance. And number three, chemicals are used to filter other chemicals. That's crazy.
Bioremediation broadly refers to any process wherein a biological system, living or dead, is employed for removing environmental pollutants from air, water, soil, flue gases, industrial effluents, etc., in natural or artificial settings. Some types of bioremediations include microremediation, which involves bacteria, microalgae, and/or fungi. And the other type is phytoremediation, which involves living/dead plants. We are using bioremediation in order to come up with a natural, efficient, and cost-effective method to filter the textile wastewater that even a small-scale dyeing factory can afford and perform.
Last year in phase one, the research objective was dye color remediation. Last year I worked on finding a solution to this problem with bioremediation using organic materials chosen by their properties with a research scope of just treating the dye color. But in phase two this year, we've expanded the scope to find organic materials which are effective in treating the pH, salinity, and hardness levels of textile dye wastewater.
To find the organic materials necessary for our bioremediation process, we did lots of research and rounded up 11 different materials. They include peat moss, which is commonly used for gardening, banana peels, coffee grounds, cattails, bentonite clay, which is available almost anywhere on the earth, coconut coir, moringa seed powder, a natural flocculant, mushrooms, activated charcoal, which is very porous, lime peels, and rice husks.
I'd like to talk about phase one, which was completed last year. The objective was to use organic materials to effectively reduce the dye color of textile dye wastewater, as said before. I incorporated organic materials into various concentrations of mild reactive textile dye solutions and studied their performance when applying directly, wrapped in cotton cloths, and set them up as material combinations. To collect the data, I dipped paper strips into wastewater samples, took pictures of them, and then used the GIMP or GNU image manipulation program to calculate the dye saturation of the submerged portions. As per the data, the moringa seed powder reduced the dye color exceptionally well. And here are some pictures of the work I'd done last year, as well as some data.
This year, phase two, we started with simulating the typical dyeing process to obtain the wastewater and expanded our bioremediation scope for treating pH, salinity, and hardness levels. Textile dyeing factory use dyes from mild reactive to high reactive based upon the desired color, shade, and depth. The chemicals in the wastewater vary based upon the dye they use. The salinity, pH, and hardness, on the other hand, are common issues with all dyeing wastewaters, and in addition to the chemicals present in the particular dye. Our goal is to find the organic materials which can effectively remediate the salinity, pH, and hardness levels in the dye wastewater. So to begin with, we simulated the textile dye wastewater using the typical dye factory process using mild reactive tie-dye powder and household food grade chemicals.
To start, let's start by looking at the source. When the cotton grows in the plant, it produces a natural wax that attracts a lot of impurities from the atmosphere. Starch is also added to cotton to make yarn. So the raw fabric usually contains wax and starch in it, which won't allow the dye to absorb. The first stage in the dyeing process is RFD, ready for dyeing, also known as the boiling process. In the process, the fabric is boiled in water, caustic lye, hydrogen peroxide, and wedding oil. An alkali medium is necessary to remove the wax and starch, and that is the reason why you add the caustic lye. Hydrogen peroxide is used to make the fabric brighter, while wedding oil is to wash away all the impurities. Following this is a hot and cold water wash. Then to convert the fabric back to a normal pH, we need to neutralize it using acetic acid, or vinegar in this case.
Following this step, we finally get to the dyeing process. Salt and soda ash are added to the fabric and water at 60 degrees Celsius, and the dye solution is later added. The salt acts as an exhausting agent as it forces the dye molecules out of the water and into the fiber. The soda ash, on the other hand, acts as an alkali medium and also a dye fixative. Following this, we do once again the hot and cold wash, and then convert the fabric back into a pH level normal. We need to neutralize it using acetic acid, also known as vinegar. To avoid permanent color bleeding, the dyed fabric needs to go through the color fixation process. We have collected the output from each step in accurate proportion and combined it into one container and used it for this study.
Now let's go over phase two with the actual experiment. Our goal is to study the organic materials capable of balancing the pH, salinity, and hardness and apply them into the simulated textile dye wastewater to see how effective they are. Let's start with case 1, treating the textile dye wastewater with the 11 selected organic materials individually. On each glass, for 200 milliliters of wastewater, 10 grams of organic materials are added and allowed to settle down overnight, and later we measured the salinity, pH, and hardness, then we compared them to the control sample. Now a note about hardness. Due to the chemicals in fine organic materials getting suspended into the wastewater, we couldn't filter the remediated samples to the microscopic level to measure the accurate hardness. For this reason, we had to exclude the hardness parameter in our experiment.
For studying case 2, we selected the 8 best performing organic materials out of the original 11 from case 1 and created 6 combinations as a mix of 2 materials each, based upon their individual performance on salinity and pH. We then treated the wastewater with these 6 material combinations. They include moringa seed powder with coconut coir, mushrooms with peat moss, banana peels with coffee grounds, cattails with peat moss, bentonite clay with coconut coir, moringa seed powder with activated charcoal. Then we tested the same way as we did in case 1.
Now let's go over the final case, case 3. We selected 6 of the best performing organic materials from case 2 and created 2 combinations of 3 materials each based on the performance of salinity and pH from the previous case. In this scenario, the 2 combinations were moringa seed powder, bentonite banana peels, and mushrooms versus peat moss, cattails, and coconut coir.
This slide shows our data collection method. Material is used to simulate the textile dye wastewater and the safety measures used. Feel free to pause this to observe this carefully.
So let's go over our observations, starting with case 1. It was quite a challenge in adding the cattail, coconut coir, and peat moss into the wastewater test samples due to their tendency to expand and absorb the water. Activated charcoal turned the sample into a dark and chunky solution. However, peat moss reduced the salinity and pH levels exceptionally well by 34% and 42% respectively. Surprisingly, banana peels reduced the salinity pretty good by 18%, along with activated charcoal and bentonite clay. Lime peels reduced the pH by 41%, followed by coffee grounds, which reduced it by 37%. As you can see here, there are some graphs that you could feel free to pause and take a look at it if you want.
For case 2, when peat moss was combined with other organic materials like mushrooms and cattails, its overall performance for salinity reduction was lower than its individual performance, going from 34% to around 17 to 24%. However, it showed better pH reduction, going to around 43 to 46% reduction. Moringa seed powder with coconut coir and banana peels with coffee grounds also perform well for the salinity and pH reductions. Once again, you can see the data and graphs here.
So now the final case. Once again, peat moss wasn't as effective in salinity reduction as it was individually when combined with cattails and coconut coir. We are assuming this was because in case 1, we applied 10 grams of peat moss into 200 milliliters of wastewater, but in cases 2 and 3, we only applied 5 grams of peat moss to ensure that the amount of organic materials added were constant. The combination of moringa seed powder, banana peels, and mushrooms, on average, was 9% to 10% less effective than the other combination in salinity and pH reduction. And here's some more graphs, as you can see here.
In conclusion, our study was conducted by simulating the typical dyeing factory process using mild reactive tie-dye powder with food-grade and domestically safe equivalent chemicals to obtain the wastewater. As per our study, peat moss was the best performing organic material in the reduction of salinity and pH of textile dye wastewater. Peat moss proved to be the most effective in reducing the pH as it commonly grows in bogs, which are known for their natural acidity.
Activated charcoal also performed well in salinity reduction, while lime peels and coffee grounds were good at reducing the pH. In case 2, the peat moss and mushrooms combination performed the best in salinity and pH reduction, while in case 3, the peat moss, cattails, and coconut coir combination performed the best. In phase 1 last year, I mentioned the moringa seed powder performed exceptionally well in dye color remediation, and it did a good job in pH reduction this year. From our findings, a cost-effective and efficient filtration system using organic materials could be developed and can be scaled to be used in real textile dyeing factories. This could promote the recycling of water and the environmental effects could be reduced greatly.
For our possible future studies, the coffee filter papers and the tea strainers that were used in the filtration of the settled organic materials in the solution weren't effective enough. They couldn't filter out the finer materials that got suspended within the solution, which interfered with our measurement of hardness. If we get the opportunity to work with a professional laboratory on the filtration process, we'd like to include hardness as a parameter in our next study.
So we're also considering stage-by-stage filtration, wherein we run textile dye wastewater through several layers of our organic materials. Each layer contributes in reducing something out of hardness, pH, salinity, and dye color. This would model a complete bioremediation filtration system for treating textile dye wastewater. Here are some of our sources and some of the pictures of the work we've done this year, and some more pictures. Thank you for your time. We hope you enjoyed.
Bye.
Bye.